Guys, in our last class we discussed about how to find the area of a circle using integration. Today we are going to discuss about another application of integration. There are so many applications for integration, and here I am taking just the cone, how to find the volume of a cone using integration. See, consider a cone. This is your cone. Let its radius be let its radius be r, and let its height be h. So you need to find the volume of this cone with base radius capital R and height h. How will you use integration for this purpose? For that, I'm just taking a section here. See, there's a section, circular section here. Actually, it's a small cylinder of thickness dx. See, this section is like this. It's like a disc of small thickness. See, here you can see it's a small disc with a thickness dh. This will be dh, and let this radius be r, small letter r. See, these two radius are different. Here, this section on expanding, you will get a structure like this, a disc of radius r and thickness dh. See, here the radius will be r. Now, suppose I just take that triangle . Suppose this is your triangle. See, this right triangle, I just redrawn it here. So this will be the radius r, and this will be the radius of that cone, and this whole length is the height of the cone. And let this height up to the this point is the vertex, the distance from the vertex to the section we took, let that height be h. You know that these two triangles are similar. I'm naming that triangle as A, B, C, D, E. You have triangle ABC is similar to triangle ADE. See, these two angles are 90, and this one is parallel to this one, so these two triangles are similar. So you can write R by H is equal to capital R divided by capital H. You just remember this equation. Name it as equation number 1. Now, the volume of this cylinder, this is actually a cylinder of small thickness dh and base circle of radius r. So its volume dV will be base area into height. Clear? Here the base area is pi small letter r square. It is a circle, so its base area equal to pi r square, and the height is dh. So this is the small volume. Name it as equation number 2. Now in order to find the total volume of this cone, that is your V, you need to integrate dV. So here the variable is h. See, this is your variable h. So you need to put the limits of the integral as 0 to h. Since its least value is 0 and the highest possible value of the cone is h. So you have to put the limit as 0 to h dV. Now on substituting, you get integral 0 to h pi r square dh. This is equal to, V is equal to integral 0 to h pi, see here in this case of r, in this place, instead of writing r, you can put here, see, r can be written as r h whole divided by h. So in the place of r, small letter r, you can write rh by h. So again this equation become r h by h whole square times dh. Clear? I'm just erasing these things. You'll get. So on expanding this equation, this one, this implies V is equal to 0 to h pi, here squaring all the terms, you will get h square by h square dh. Now see, this pi r square and h square is constant, which is the radius and height of the height of the cone. So it won't change. So you can take it as constant and place it outside the integral sign. So h square integral 0 to h square dh. Now the volume, this is equal to pi r square divided by h square. What is the integral of h square dh? Which is h cube by 3. Now you have to put the limits. Lower limit is 0 and the upper limit is r. Now substituting the upper limit and lower limit, you will get pi r square h square into, first you have to substitute the upper limits. The upper limit here it is. It's not r, it's actually h. So substituting, you will get h cube by 3. There is a 0 cube by 3. No need to write it because it becomes 0. So cancelling this h square and h cube, you will get pi r square h by 3. So the volume of the cone is V is equal to 1 by 3 pi r square h. See, so the volume of in any cone of radius r and height h is 1 by 3 pi r square h.